Welcome. This is Professor Nathan Weezy of Marquette University. In this section, we're going to talk about the PI controller, or better yet, the proportional integral controller. Okay, in time domain, simply what this looks like in the frequency domain here is that we have a proportional gain, Kp, and we also are integrating with a gain for the integrator, Ki by S. And that's what it looks like in the S domain or the Laplace domain for a PI controller. So equation 1, we have our PI controller. Now what we're going to do is convert the PI controller to the Z domain by using this Tustin transformation or approximation. So this S is going to go up into here, and this whole thing will come down and be the result of plugging 2 into 1 will be equation 3. All right, so our PI controller in the Z domain using the Tustin approximation looks like equation 3. Now I know there are other ways to get this, but this is just one way that I've done to get this. Now what we're going to do is try to design a controller for a plant. The plant will be equation 4, just arbitrarily 10 over S plus 1. This is a low-pass filter. We're going to try to design a controller for this plant. So we're going to design it in the S domain, continuous time, and then basically convert it to the Z domain and check the performance of it. All right, so here's our controller. And again, this is the same as equation 1. I just pulled out a gain of Kp that's common to both terms and got a common denominator. So it's easy to see in a PI controller that you have a 0 at the origin here, or sorry, a pole at the origin, and you have a 0 right here. It's pretty easy to see when you factor it like that. Now, what we're going to do is multiply the controller by the plant. So we have this structure here where we have the error being fed into the controller. The controller is outputting a actuation signal to the plant spits out the output, and we feed it back here. So GOL will essentially be GC times GP. And you can see we land with equation 6. Now, we're just, to make this stuff simple for now, we're going to look at a bunch of different values later, but I'm just going to essentially make the 0 of the PI controller, which is this value here, equal to 7, so that we have a pole 0 cancellation. So I'm going to make Ki by Kp equal to 7, and that's said here in equation 7. If I do that, then they'll cancel, the 0 and the pole will, and I'll be left with, for an open loop transfer function of this. Well, guess what? That's just simply an integrator now. And if I look at the gain of GOL, an integrator just looks like this as you sweep frequency. It's just dropping at minus 20 dB per decade. And what I can do is pick the bandwidth very easily by picking the point at which it crosses through 0 dB. And how am I going to do that? Well, I'm going to calculate the gain of this and equal it at 0 at the frequency in which I'd like to set the bandwidth. So how do I do that? Well, the gain of GOL, the gain of it is simply 10 Kp by J omega, but we're just doing J, so, or sorry, the gain, so the J goes away in omega. So that's our gain. And we're going to set this equal to 1, the gain of 1, which is 0 dB, at the frequency that we desire. So essentially, if I plug all that in, what I get is equation 9. So it'll give me my gain for Kp. Kp is a function of F band. Band I'm going to select. I'm going to select here to be 100 hertz. So that's going to be the bandwidth of my controller. So if I look right here, this point here will be 100 hertz. Excuse me. All right, so if I go ahead and calculate Kp with 100 hertz, 2 pi 100 hertz by 10, what I'll get for Kp is right here, 439.823. Okay, and if I calculate then back calculate Ki, I get 62.83, and this now becomes my controller. I can feed it in to the gains for the controller. All right, now what I'm going to do is convert this controller from Laplace domain to the Z domain with the Tustin approximation. And I'll land at equation 12, and that's the controller I'm going to have here. All right, I can also calculate the closed loop response in the S domain and then convert this to the Z domain with the Tustin approximation. I want to look at where the poles and zeros land up here on the Z domain map. All right, if you look at this, I only am going to have one pole, and where does it land? Well, it lands right here. Approximately, the pole is at, I don't know, 5.1, somewhere in there, 5.2. You can see it up here. It matches here with our plot. All right, if you look at that, that's a damping ratio of essentially 1. And so I should get a good response. And the natural frequency here is going to be 0.2 times pi by t. So that's a line for the natural frequency. So I should get a good, nice response for this selection of pole cancellation and doing 100 hertz bandwidth. So if I take a look at the step response, this is what I get. Nice, clean, very well damped response. And it goes right up to 1, and it takes approximately to get there 0.01 seconds. And this does have a kind of a loose correlation to bandwidth. Remember, I picked 100 hertz, and I'm essentially getting up to the value I stepped in and 1 over the bandwidth, which is interesting. There's a loose correlation between this and this response time. Cool. All right, so we designed our first controller, got a great response, but let's try to kind of look at the space of Ki and Kp values that I could use. Now, the previous two controllers, I had just Kp or I had just Ki. There's only one variable you could sweep, but now you got two, so the design space starts to open up, which means that essentially you as a designer have lots of options for Ki and Kp pairs. So how are we going to basically find what pairs to look at? Well, a very nice way to do this, again, is with the root locus plotting platform. Now, what I've done here in this plot is I've swept for various KPs and KIs. And let me explain how I did this. So I did root locus, and what I did is I have 3 sets of lines. I have a fixed KP. So all 3 of them are for a KP of 5.75. And then I have different ratios of Ki to Kp. Essentially, these are different. I'm keeping Kp fixed, but I'm sweeping different values of Ki for the fixed Kps. And so, for instance, for blue, I have a Kp of 5.7, and this ratio is 30. And there's a lot of different numbers you could have for a ratio of 30. And you can see this is the trajectory for blue. And similarly, I have one for red. One will come in here, and the other one will go out like this. And then lastly, we have yellow or this orange. So one will come in like this. The orange one will go out like that. Okay, so these are just various values of Kp and Ki. And you can pick any one of these. Now, the thing I want to note here too is we're not in the Z domain in this map. This is actually the S, the frequency domain. So when we're looking at different values here, slightly different than the pole zero map in the Z domain. So when we're looking at these radial lines here, these are damping factors now. This is essentially zeta. So for instance, if I had a pole right here, I'm on the line for perfect damping, right? If I have a line here, or my pole is here, this is a damping of 0.9. So it's the same if I had it over here. This is a pole for damping ratio of 0.9. So it's a little bit different than the pole zero map for the Z domain, but essentially they're telling you the same thing. How much damping do you have, and what's the natural frequency? So the other thing here is if you look at these circular contours here, these are for fixed natural frequencies. Like this one's 100, this one's 80, this one's 60, this one's 40, etc. So what I will say, when you're on this map and you're looking, the further you go this way, or in other words, the higher the natural frequency, the faster the response. Okay? Now, the other thing is the further you get away this way, or kind of this way, angularly away from this line here, you have less and less damping. For instance, if you're up here, that's a damping of 0.2. That's bad news. So it's a little bit different space than the pole zero map in the Z domain, but essentially, again, it's telling you the same thing. So where would you like to be in general? Yeah, you'd like to be on this line and faster to the left, right? And as you go this way, you get less and less damping. Okay, so it kind of gives you an idea of where you want to be. Now, what I have done is pick 3 arbitrary values here for Ki and Kp. So I have one here, here, and here. And these are complex conjugate pair poles. So if we go back here quick and look at our closed loop response, we have a complex pair pole. All right, so what I've done is plotted the step response for these 3 points. So this blue, this red, and this orange. And these are the associated Ki values now. So once you pick a point here on the root loci plot or the S domain pole plot, you can actually calculate then what Ki is. So these lines represent fixed Ki Kp ratios. And once you pick one, then Kp is fixed here, you can figure out what Ki is. So for instance, this is hard because, I mean, you have an infinite space to look at. It's like, where do you even start looking? Oh, you just lay down some lines and start looking where you want to be. So here, these are fixed Kps, like I was saying, and those 3 points that I picked, these are the Kis. And of course, if you look at these damping ratios, let's try to take a look at these quick. So like this one's 0.7, this is 0.56, here's 0.8. They're not bad in terms of looking at step response. So here's the worst case one. It overshoots, undershoots little, and settles down. And as we go in closer towards the just having a real part, we get more and more damped, like this blue one, which is here, is closer and has more damping. Okay? All right, so now you kind of have an idea of how to design a PI controller, at least spatially, where you want to put the system poles, okay? And you want to get really good at calculating the poles in the root locus plot. All right, so the next thing what we're going to do is take a look at these responses now that I have these controllers in the S domain. That means I have Kp and Ki, but I looked at them in continuous time. Let's see what they look like in the Z domain. So I'm going to pick a sampling time first. I picked, looks like 10 milliseconds, and I'm going to convert these through the Tustin approximation. So I took GC, I plugged in S equals a Tustin approximation, and I'll have 3 controllers because I had 3 different Ki, Kp values. And these are the 3. So 17, 18, and 19. Those equations are the 3 different controllers using the Tustin approximation, and they're put into the Z domain. All right, if we take a look now at our response here in time here, you can see that, yeah, these track pretty well to what the continuous time looked like. And of course, again, yellow, which had less damping, of course, rings more and overshoots more and it undershoots more compared to the other 2. So these track pretty well to what we saw here in the continuous time response up ahead. Okay, and this concludes our design process for the PI controller. Thank you.